Hello, this is Sharon from SAS Statistical Programming. In this tutorial, we're going to look at the measures of fit for the multiple linear regression model, R-square and adjusted R-square. R-square is the statistical measure that represents the proportion of the variance for a dependent variable that's explained by an independent variable or variables in a regression model. As more predictors are added to the model, at least those related to the outcome variable, the fit of the model improves, and as a result, the R-square increases. It turns out that even when a variable not related to the outcome variable is included in the model, R-square still increases. The R-square is basically inflated as the number of predictors increases and is an overestimate of the relationship between the outcome y and the set of predictors. Therefore, the more common measure of fit is the adjusted R-square, and is calculated as follows. N is the number of points or cases in your data sample, and the K is the number of independent regressors, or the number of variables in your model, excluding the constant. The adjusted R-square include a penalty for adding more predictors. The formula also takes into account that as the sample size n increases, the penalty for using k predictors becomes smaller. In other words, as the sample size increases, the value of adjusted R-square approaches R-square. It should be noted also that adjusted R-square is better estimate of the fit in the population. Now let's look at the program for measures of fit. Again, I'm including the same lab name and the proc format as well as data step to create the same template data set as we used for analysis in last tutorial, which is AS_1, and this is the permanent data set we used before. Okay, so let's run this part of the program to have the data ready. All right. Let's look at the first proc-reg program. This part of the program is exactly the same as I showed you in the last tutorial. Let's run this proc-reg program, and then let's see the output. Okay, in this output, let's first look at the two statistics. One is adjusted R-square, is this number, and another one is root mean square error, is this number. I already copied those two statistics into the code window here for later comparison. And then let's look at the parameter estimates. We already know for the three variable, tutor, parent education for college, and live with parents, for those three predictors, they are not significant as the level of 0.05. But in this model, I still include those three predictors. In this model, by including 7 predictors, we have this two statistic here. And then I include a second proc-reg program. The target variable still rescore. So instead of including 7 predictors, I include 4 predictors, 1, 2, 3, 4. That means I dropped the 3 non-significant predictors from the second model. Okay, let's run this part of the program and see whether there's any change between the root mean square error and adjusted R-squares. This is the second model with only 4 predictors. Okay, this model degree of freedom is 4. And then for the root mean square error, we got this number, and for adjusted R-square, we got this number. Again, I copied those two statistics into the code window to do a comparison. Now we can compare the two models. One is with the 7 predictors, and another one with the 4 predictors. With 7 predictors, the adjusted R-square is this number, 0.6874, and for 4 predicted, is 6871. We can see by dropping 3 non-significant predictors, there is essentially zero loss of accuracy. And also we can compare the root mean square error for the 7 predictor model as well as the 4 predictor model. The standard error of the 7 predictors regression model indicates that on average, the estimate of risk score will miss the actual score by 9.83835. When dropping 3 non-significant predictors from the model, the standard error is 9.84265, indicating with 4 predictors model, the predicted risk score will on average miss the actual risk score by 9.84265. We can conclude that by dropping the 3 non-significant predictors, there is not much difference for the adjusted R-square as well as the root mean square error. Okay? Based upon the combination of the hypothesis tests and the measure of fit, we can see the best model would be 4 predictor model. Okay?